So we are going to start with chapter 3 of complex analysis by Zill. And in this chapter consists of the calculus of the complex function. Like we do in calculus, we apply derivatives, limits, and integrals to the function. Although we define in this video the limit definition of derivatives to complex function, but many of the things of derivatives, such as the product rule, power rule, the chain rule, will be same in this complex variable functions as well. So it will not be a big deal for you. So our first topic in this video we're going to start is derivative of a complex function. So now I'm going to define it. Suppose that the complex function is defined. Suppose the complex function is defined in a neighborhood of a point z0. We have a complex function. I try to figure things for you as well. We have a f of x, f of z as a complex function, and we have a point z0, and we define it, the function f of z, at the neighborhood of the at a neighborhood of point z0, right? So this is the one of the graphical idea of it. Okay, if so, we can define it as f dash of z is equal to the limit delta z approaches to z f z plus delta z minus f of z over delta z. Okay. Remember that the derivative of a complex function is denoted by f dash of z. Okay. So here we have took a point z0, so we'll write z0 here, or the derivative of function, the derivative of complex function f of z not exist only if limit exists. So remember that the existence of the limit is very, very important. So unless this limit z0 approaches to z exists, our function is differentiable. Otherwise, it is not differentiable. So this is our key formula. F dash of z0 is equal to the limit delta z approaches to 0, f z plus delta z minus z0. Here the point is z0 minus z. F of z0 is equal to our delta z. So this is our formula of, this is the same formula of differentiation we read in calculus of real numbers. So I don't think so it will be a great deal for you to remember this formula. So it is a very, very important formula at a point z0. Okay. So okay. So so here we have an example. Find the derivative of f of z is equal to z square minus 5z. So the formula of the differentiation of a complex function is f dash of z0 is equal to limit delta z approaches to 0, f z plus delta z minus minus f of z0 over delta z. So in this formula, we first replace z0 by z, because in our given function they have used the point z, not z bar. So not z dot. So we will replace z0 by z. So the formula becomes z is equal to limit delta z approaches to 0, f z plus delta z minus f of z over delta z. So this is our formula. So now we are going to find, so in first part we will do that z plus delta z minus z. So minus z. So now we'll plug in the values here. So in place of z, we write z plus delta z whole square minus z plus delta z. In place of this, here in this, and now in place of f of z, we write f of z as it is, minus z square, or minus and minus become plus 5z. Okay, I hope you understand this step. Now we open the square of z plus delta z, where it becomes z square plus delta z whole square plus 2z delta z minus 5z plus 5, minus 5 delta z minus 5 delta z minus z square plus 5z. So there's a lot of cutting here, so we'll cut here. So minus z square cuts with plus z square, and plus 5z is cut with, cancel with minus 5. So our equation becomes 2z delta z, 2d delta z plus delta z square minus 5 delta z. Now we put the value of this side into our equation like this. So we will get in the end f dash of x limit delta z approaches to 0, and then this value delta z plus delta z square minus 5 delta z over delta z. Okay, now okay, delta z. So you can see that the term delta z we can take common from the above all terms, right? So delta z is equal to 2z plus delta z minus 5 divided by delta z. So now again we cancel delta z up and down. We get f of z limit delta z approaches to 0 to z plus delta z minus 5. So in place of delta z, if we put 0, and now we are applying the limits here, if we have a empty slide. Okay, so this is an empty slide. So f dash of x is equal to x limit delta z approaches to 0. We have 2z plus delta z minus 5. So applying the limits, after applying the limits, delta z approaches to 0, we get f dash of x is equal to 2x minus 5. So this is our function f dash of x. Okay, this is our function. This is we have used that formula. We have used this formula, this formula. Very, very important things to remember. So the thing to remember here is this thing. Okay, so you should write this thing very carefully in your notebooks. Now, our next topic is, so first I will raise that. Okay, so the next topic is the rules of differentiation. So the rules of differentiation is same as we did in calculus. The rules of differentiation of calculus of real variable carry over to calculus of complex variable if we have g and f be complex functions and differentiable at a point z, differentiable at point z naught, then at a point z naught and a point z, and c is any complex constant, then these things happen. Number one is very famous, very important, is over power rule. How this rule works like this. Okay, for first is over constant rule. We use for the first one rule as well first, which is this. If we have to derive c, then the c goes out, or we have derivative c f of z, then c goes out and f of z as it is. So we will not apply derivative of complex function to any constant. Okay. Similarly, our second rule is sum rule. Okay, if we have to take the derivative of two complex functions f of z plus and minus g of z, then it will be written as f dash of z plus minus sign as it is, then f of z as well. So if in the differentiation of two complex function and they are adding or subtracting with each other, then we are not changing their sign, so that the sign will come as it is in sum rule. Okay. Number 3 is over product rule. If we have to take a derivative of two complex function, we should write as then we will write first function as it is and take the derivative of second function, plus second function as it is and take the derivative of our first function. This is a very important formula. Number 4 is over power rule. If we have to take a derivative, we have to take the derivative of a function f of z having some power n, then this power will come to first, and f of z n minus 1, we take the power of f of z to the jumps to first, and we get minus 1 from it, and now take the derivative of f of z. Remember that we again take the derivative of f of z. Now our third rules are we are going to proceed everywhere. So our I think so sixth rule is very famous over quotient rule. Quotient rule. So if we have to derivate two complex function, but they are in this form, then we will do it as we take the scale of the denominator, and the denominator will write as it is, and take the derivative of first function. I don't know, I'm writing x. Everywhere we have to find the z. See, we have a complex function minus sign f of z as it is, and take the derivative of the second function like this. So this is our formula of quotient rule. And our last and very important is our chain rule. These are very similar and same as we read in our calculus of real numbers. So we have to take the derivative of chain rule, then we will write as f dash f of g as it is and g dash. Okay, so these are our very important rules. Okay, remember them by heart. There is nothing very difficult in them. So this is our question here. So these are 4 or 3 parts. I will do some of it and you will do the rest of them. So for f of x, we have to find a differentiator. So in this question, we will apply the rules of differentiation now. So f dash of x is equal to, in the first term, you can see that we use in the first question, we will use the power rules in the first question. So first part, power rule. So the power of z dot becomes as it is, jumps out, and 1 minus, and get minus and subtract 1 from that power, and which is 3. Okay, again the same 5 as it is, dot the power of z and subtract 1 from the power of z, we get 2 plus z, power of z as it is, and subtract 1 from the power of z. So now we get 12 z cube minus 15 z square plus 2 z power 0. As you know, the power of any number becomes 0, then it is equal to 1. So this is the derivative of our function f of z. Now it solved its second part. You can see that in the second part, we have to apply our quotient rule, because we have two functions and they are dividing with each other. So we are going to divide it. So we are applying to the quotient rule. So take the square of the denominator, and denominator will written as it is the derivative of first, and in the derivative of first function we have z square. So we take the power of z as it is and subtract from the power of z, we get 1 minus z square as it is. And now that for derivative of 4z plus 1 is 4. How? Because the derivative of z, any constant function, is 0, and the derivative of this z, so we have power 1, and subtracting 1 from the power is z0, and z0 here is equal to 1. So we'll get 4. Okay, so the derivative of 4z plus 1 is 4. So in the end, we will get 8z plus z square plus 2z minus 4z square over 4z plus 1 square. And then for 8z square minus 4z square will come 4z square plus 2z over 4z plus 1 square. So this is the answer. This is the derivative of z. So the third part, C part, will be, okay, in this part we will apply the power rule, but power rule in a good manner. So take the derivative, the power of the function down, and subtract 1 from the power, we get 4. And now take the derivative of inside. So the derivative of inside function is the derivative, the iota here is constant written as it is. The power, the derivative of z2 is 2z, while the derivative of 3z is z function as it is. So our derivative becomes z power iota square plus 3z power 4 z 2z plus z. So this is the derivative of our last function. So these are our all complex function, and would have taken their derivative. So our next topic is over. So here we have not differentiable condition. So till now, if you think of that, if every time we have a complex function and take the derivative of it, it will always become differentiable function. Is every complex function is differentiable? Then the answer is not. It is not possible that every time we take the derivative of a complex function and get differentiable. It means there are conditions, there are possibilities when our function does not become differentiable at a point z naught. I always remember that we check the differentiability of a function at a point. Okay, so the first condition the function is not differentiable is that if its limits does not exist. If its limit does not exist, right? For example, in the formula, if you remember that in the formula x delta z approaches to 0, f of z naught plus delta z minus f of z naught in over delta z. In this formula, and every time I have written that delta z, if limit exists, provided that limit exists, so it is the condition that in this formula, if we want our complex f of x f of z to be differentiable at z naught, we have to prove that its limit this exists as at z naught. Okay, so the second condition is that equal to the same number, the derivative of a function equal to the same number, equal to the same complex number from any direction. If we take the derivative of a function, then it will be equal to or approach to the same complex number from any direction. For example, just look at it from graphically that we have this is over imaginary plane and this is over complex real plane, right? This is over complex plane and this is over real line and this is over imaginary line, right? So if we have a function f of z approaches at a point z, then if I should change the color, then we will check the function f at point z from four direction. If it is differentiable at all the four lines at all the four directions, then it is differentiable. For example, if we check the function is differential from this side or from this side, where delta z is equal to delta x in this real line, in this real line, we have a function z f of delta z which is approaches to z, then it is on real line, it means it is equal to delta z, then it means any line parallel to our real line f of z should be approached to same number from right side or from left side. Similarly, if I draw again a complex real line and over so this is our function z, then on a line parallel to y axis or imaginary axis where f of z is equal to delta y, then from up and down or a function f or a function z, function f should delta or function delta z should approach to the same value z, then our function is differential. In short, this is our function. From if we have this plane, I should make it from this is our complex plane. We have a function which is differentiable at z naught, then it is differentiable and it is differentiable from any side. It is differential from this side, this side, this side, this side. Then we will call from, because it is differential from any side, then we will call it is over differential function at a z. If the function z is not differentiable from right side or from up or from down from any one side, then our function is not be differentiable function. What does I mean from all this story is the example. From this example, you will get the right idea what I'm trying to explain you, which is that show that the function fz is equal to z plus 4 iota y is not differentiable at a point z. So now we have a point z, and we are going to prove that our this function is not differentiable at a point z. So now, the formula of the differentiation, as you know, that is f dash of z. If a function is differentiable, then we have to prove that the limit delta z approaches to 0, f of z plus delta z minus delta z over this. So, right? Till now, there's no any problem. Now, we will, step 1 is z plus delta z minus f of z will be written as, so in place of this, we will written as x plus delta x, 4I is constant, take out of it, and y plus delta y minus x minus 4iy. Okay, So now x plus delta, sorry, x not, in we have to write x here. So x plus delta x plus 4iy plus, yeah, we should write xy here. So plus 4i delta y minus 4iy. So we have just opened the brackets till now, nothing special. We have cutting here. X is cut with minus x and 4iy minus 4iy. So this is cutting here. So we have in the end x plus 4i delta y. Okay, and remember that in this question, our delta z is equal to delta y plus I delta. Okay, delta y plus delta x plus I delta y. So now we are plugging over these values in our formula. We will get dy is equal to limit x delta x approaches to 0. So we get delta x plus delta 4I delta y. In place of delta z, we will write this x plus I delta. Now we are going to check over limits or over that over the behavior of function along two direction in complex plane. So the direction is along. Okay, we have the slide over the function. We should take over again the new slide. So we are back with our new slide. So we this is our question becomes, now we are check this function we have in the complex plane. As you know, in complex plane we have two directions. We will check it along the over x-axis, and we will check this function along y-axis. So how we will check that the function is differentiable or not in this way? Like the first case is along a line parallel to x-axis. So in a line parallel to x-axis, we have f dash of z naught is equal to lambda in z. Delta z approaches to 0. So we will in this formula we will in over a real axis or in over y-axis x-axis over the value of our delta y is equal to 0. So we will take only the value of delta x, right? Okay, so you can see that delta x is cut with delta y. So we get the answer of it as if, okay, sorry, we will again. Okay. Wait for a while, we have to be and okay, so this here, okay, we will get in the end 1 as an answer. Okay, now if we approach along a line, so our function f of x along the real axis approaches the approaches the real number 1. Now we are going to check a line our function f of x at along the line z axis along over, so not z axis, along over y axis or imaginary axis, or along a line parallel to y axis. F of z is equal to delta z approaches to 0. So now we are right in you know that in our this imaginary axis over delta z is equal to 0. We'll take only the value of delta. So write as 4i delta y over I delta y. So you can check that delta y cut, so delta y I is cut by I. So we have we have again 4 as answer. You can see that our function along x-axis approaches the value 1, while from the y-axis approaches the value 4. So from y-axis it approaches to 4, and over z-axis it approaches to value 1. So over this function we have proved that over this function f of z is equal to f of xi is equal to x plus 4iy is not differentiable. Is not, because it gives different values along x-axis or imaginary axis, or from y-axis or from real axis and from imaginary axis. So this is our video.